Homework from last night, page 305. We want to go over two questions, number 3 and 10, starting with number 3. Explain why the frame of reference affects the calculated value of an object's gravitational potential energy, but not the change in its gravitational potential energy. Good question. Okay, this comes back a little bit to the quiz that we just did, not the second part of the question, the change in potential energy, but certainly the first part. You were asked in that quiz to find the potential energy of the ball, or whatever it was, the ball, relative to the top of the table and relative to the floor. In the end, the potential energy is always defined relative to something. Now, sometimes we just say, oh, what's the gravitational potential energy of this car? Well, what we mean is relative to the earth, relative to the ground, if we don't specify. But technically, there's always got to be that reference point. It's just that usually it is the ground, so we sometimes don't say it. Okay, if your reference point is something else, then we should specify what it is. Bottom line is, objects have different potentials to fall depending upon where we're measuring it from. In that quiz, you had the ball on the desk. Let's say you had the ball on the desk. Well, it has zero potential to fall to the desk, but it does have potential to fall to the ground. So we have to define where it's relative to the desk or to the ground. Does it have potential to fall somewhere, or does it not have potential to fall somewhere? So that's why we have to have a frame of reference, and that's why it affects the calculated value of the object's gravitational potential energy. But why does it not affect the change in gravitational potential energy? Well, let's look at it this way. If I measure the potential energy of this pen relative to the desk, okay, it's 0. I measure the potential energy of that pen relative to the floor, it's 5. So relative to the desk, the potential energy is 0. Relative to the floor, the potential energy is 5. Let's say I lift that desk, or not the desk, but let's say I lift the pen up. Okay, it goes up into the air. I give it 3 more joules of potential energy. Okay, so I've given it an extra 3 joules of potential energy by raising it a certain height. Now, when I raise it a certain height, how much further is it above the desk than it was before? Let's say a meter. How much further is it above the ground than it was before? A meter. Right? Its height is not the same relative to the ground as it is the desk, but the change in height is the same relative to the ground as it is the desk. So if I gave this pen an extra 3 joules of energy relative to the desk, then its potential energy would be 3 joules. If I gave it an extra 3 joules of energy, its potential energy relative to the floor would be 8 joules. So regardless of what I measure what my frame of reference is, the desk or the floor, the change in potential energy is going to be the same, right? It's kind of like saying, here's an analogy for you. Okay? When I go to 7-Eleven to buy my Slurpee at lunch, I spend my $2 to get my Slurpee at lunchtime, right? So I go down there with $10. Okay, I come back here with $8, right? You guys, you rich kids, go down there with your $100 bills. You buy yourself a Slurpee. How much money do you come back with? $98, right? What's the change in money? $2. Regardless of whether I start it with 10 or I start it with $100, the change in money is $2. So it doesn't matter what my reference point there is. Now, if I'm measuring the amount of money that I have, yeah, it matters what my reference point is. But if I'm measuring my change in money, it doesn't matter what I start it with or what my reference point is. Okay? If I'm measuring the potential energy, it matters what my reference point is. But if I'm measuring my change in potential energy, it doesn't make any difference what my reference point is, what my starting point is. Okay, change is change. Right? Let's take a look at number 10 now. It says a cart with a mass of 3 kilograms rolls from the top of an inclined plane that is 7.5 meters long with its upper end at a height of 3.75 meters above the ground. You know what? I'm going to get confused by this. I get easily confused. I'm going to get confused by this if I don't draw a picture of it. So I'm going to do that now before I even read the rest of the question. Here's my inclined plane. It's 7.50 meters long, and the height of the hill, the height of it is 3.75 meters above the ground. All right. So the cart that we have rolls from the top up here, and it rolls down to the ground. There's a force of friction of 4.50 newtons. And we want to find the change in gravitational potential energy when the cart moves from the top of the inclined plane till it reaches the ground level. I'll tell you what, the easiest way to find a change in gravitational potential energy is the easiest way to find a change in anything. Subtract the final minus the initial. So we're going to say delta EP is equal to EP final minus EP initial. In other words, it's going to be MGH final minus MGH initial. Now, MGH final is 0, right? Because it ends up on the ground. So it's going to be 0 minus M, 3 kilograms times 9.81 times the initial height of 3.75 meters. What do we get when we multiply those three numbers together? 3 times 9.81 times 3.75. It's going to be negative, right? Negative 110.363 joules. Anybody else agree with that? Yes? Negative because it's final minus initial, 0 minus whatever. We have a loss of energy here, right? We should round that to 3 digits. So we're going to say negative 110 joules. That's how much potential energy we lost here, 110 joules. All right. That had nothing to do with friction, by the way, right? Potential energy has everything to do with mass, gravity, and height. It has nothing to do with any other forces, including friction. But question B does. B does have something to do with friction. What's the work done by friction? Well, work is defined as the change in energy, but it's not the overall change in energy of this ball. Why? Because friction didn't cause this ball to change its energy by 110 joules. What caused this ball to change its energy by 110 joules? Well, two things. Oh, no, sorry, one thing. Gravity. Gravity caused it to change by 110 joules, right? So if you wanted the work done by gravity, the answer would be 110, equal to the change in energy, right? But if we want the work done by friction, we got to go at it a different way here. Work is equal to delta E, but I don't know what the change in energy due to friction is, but it's also equal to F times D. The force of friction is 4.5 newtons. The displacement is 7.5 meters. That's how far the ball or the car travels as friction acts on it. Hey, why am I not putting the cos theta in there? We're on an angle, right? Why am I not including an angle? I don't know what the angle is. Maybe that's why I'm not including it. Hey, I could find the angle. Here's theta. You could say sine theta is equal to opposite over adjacent. Find theta. Why am I not bothering with that? Ever? Yeah, friction is acting parallel to the hill. It moves parallel to the hill. Friction acts parallel to the hill. The angle between the way that it moves and the way the force acts is 0. 4.5 times 7 is 33.75 joules here. We're going to round that to 3 digits, 33.8 joules. How many people got that? 33.8 joules. Guys, you understand that work is the change in energy, but why? You understand why we're not using 110 joules here for the work done, even though that's the change in energy? Okay, because that's not the work done by friction. Okay, friction isn't applying the force that's causing its energy to change by 110 joules. Okay, that's the work done by gravity, not by friction. Okay, yesterday we did our little power activity running up the stairs. Okay, the work done against gravity was equal to the change in potential energy. Yep. Yeah, right. Let's spend a couple minutes reviewing the stuff that we started yesterday with, which was power. We defined power yesterday as the rate at which work is done. In other words, a simpler way to say it maybe might be how quickly work is done. When we talk about a rate, we always have time on the bottom. The rate of change of position would be delta D over delta T, velocity. The rate of change of velocity would be delta V over delta T. Okay, it would be acceleration. A rate of anything has time on the bottom. The rate at which work is done is going to have time on the bottom, work on the top. Its symbol is P, capital P, and the units for power would be, well, one we said was joules per second, and the other one we said was, what was the other set of units for power? You know this. Yep, the watts. Yesterday, our example problem was your determination of the power output of your legs. You guys ran up the stairs, and you guys found the power output of your legs. We know that power in that case is equal to work, or delta E over T. We know the change in energy of you as you ran up the stairs was, you had final potential energy. You had nothing when you started. Change in energy was potential minus 0 over the time. You guys multiplied your mass times gravity times the height of 3 meters, divided by the time, and you get varying values of power. Some of you got 200 watts, some of you got 700 or 800 watts. We saw yesterday as well that if you had a power of over 750 watts, then you're as strong as a horse for 3 seconds, or however long it takes you to run up those stairs. So our example problem yesterday illustrated, the example problem that was different for everybody yesterday, illustrated that basically, if you can do work, you can do power. Okay? Power is the rate of change of energy. It's the rate at which work is done. So get work, whether it's by F times D, FD cos theta, or whether it's by final energy minus initial energy, get the work and then simply divide it by time. If time is bigger, power is smaller, the rate at which work is done is smaller. If time is smaller, then the power ends up being bigger, right? All right, I'd like you to take a look then at 3 questions on page 325 that go with the example question that we did yesterday of you running up the stairs. Okay, let's spend a couple minutes going over the worksheet that I assigned a few minutes ago. We want to go over questions number 5, 6, and 7 from that power worksheet, starting with number 5. It says a 2-kilogram box is pushed 20 meters with a force of 50 newtons. It takes 8.5 seconds for the person to push the box this far. What's the person's power output? Remember, when we have a question involving power, we're kind of thinking work, right? We're kind of thinking work, change in energy, delta E. We're thinking work, F times D times cosine theta. Now, if we're not given an angle, we have to assume that it's pushed in the same direction as it moves. So we just drop the cos theta on the end of it. So what do we got here? Well, we know that power is equal to work over time, and we know that work is equal to delta E, and we know that work is equal to F times D. Let's get something. Get something here. Well, we can solve for work here. Force is 50.0 newtons. The displacement is 20 meters. That gives us 1,000 joules. All right, my work is 1,000 joules. I don't need this anymore. If my work is 1,000 joules and it took me 8.5 seconds to use up that 1,000 joules, then my power is simply going to be equal to 1,000 divided by 8.5, which gives me 118 watts, that would be. We should round that actually to, 3 digits, 118 watts. So you see how this question really it's just a work question, right? And then we just divide the work by the time. Questions 6 and 7 get a little bit more challenging though. 6 is a bicycle is pedaled at a speed of 22 kilometers per hour for 20 minutes. First of all, I get this kilometers per hour thing that I'm not really a big fan of. The power output of the cyclist is 400 watts. What's the average force that the cyclist applies on the bicycle? Let's convert that first of all. Okay, my velocity here is 22.0 kilometers per hour equals 22,000 meters over 3,600 seconds. And what does that work out to be in meters per second? I want to say somewhere around probably 7-ish, 6. Everybody got that? 6.111, thank you. We got quite a few givens here, so let's write these down here. 20 minutes is, what is that, 1,200 seconds? We have a power output of 400 watts, and we want to find the force. Boy, this looks kind of hard, actually. Looks pretty hard. Anybody get this, by the way? Okay, good. Let's write down what we know. We know that the equation power is equal to work over time applies, and we know that work is equal to delta E, and we know that work is equal to F times D. This is kind of like writing down, you know, if we were to write down our group B equations back in unit 1 when we had an acceleration problem. I'm just kind of putting them all together here because just so we can see them in one place, since we know this is what's applicable. All right, what can we do? We got power, we have time. Oh, we can, okay, good, this works. We have power, we have time, we solve for work. That's something. Let me just make a little bit more space here now. Work is equal to power times time. So the power is 400 watts times a time of 1,200 seconds, which gives me, what is that, 48? 1, 2, 3, 4, 480,000 joules. Okay, that's not my final answer, right? But I got something. Now I have my work, and I want to find force. The only thing that I can think of is to say W is equal to F times D, but my problem is I don't know what D is. Anybody make a suggestion as to how I might find D here? The displacement? Ben, how'd you do it? Good. So you found the displacement off to the side over here by saying D is equal to V times T, right? That's our group A equation, the first equation that we learned on the very first day of physics 20. V is equal to D over T. So we got 6.1111 times a time of 1,200 seconds. And Ben, what did you get for the displacement there? 7,320 meters, which we're going to turn around and divide 480,000 joules by 7,320 meters. And what do you get for the force there, Ben? 65.6 newtons. And that seems like a reasonable number. Good. Anybody else get that? A couple people. Ben, this force is strong with you, apparently. One of the very few people that got that question. Do you see what do you see how he did it though? Like, do you see how, not the mechanics of how he did it, not, you know, the exact equations he used and so on, but do you see that Ben probably, and the other people that did it as well, probably didn't know exactly how they were going to solve this problem when they started, but they just started, right? If you know how you're going to solve a problem when you start, that's great. Okay, I mean, in an ideal world, we'd always know, but we don't always know. That's okay. Just start with something. Hey, Ben found work. And then he's like, oh, okay, I can rearrange work equations, solve for force. And then I can get displacement by thinking back to unit 1. Right? He just thought logically at every step along the way, and it worked out. Okay, number 7. Also a bit of a tricky one. 7 says a small engine produces 6,000 joules of energy per second. What do you got there? What variable is that? 6,000 joules of energy per second. You're not told whether that's work or energy or power or force or whatever. What is it? It's going to be power. Joules per second. Okay. Now, alternatively, that's exactly what I would have said as well. 6,000 watts. But alternatively, you could have said that the work is 6,000 joules and the time is 1 second. Does that make sense? Since it's this much energy per second, it can be watts or it can be this much energy in a time of 1 second. So whatever, I'm going to go with the 6,000 watts, I think, because that's what I spotted first as well. Either one's correct, though. How far will it push a 3 kilogram object? We're looking for displacement here. The mass is 3 kilograms, and the force is 200 newtons. I think that's all we got here. Okay, so what do we have that we can try? Power is equal to work over time. Work is equal to delta E. Work is equal to F times D. And maybe we throw in a V equals D over T in there. Who knows? But the main ones we have are what we have written down there. I want to find D. Let's try using work is equal to F times D. It's the only thing I have with D in it, right? At least in this context. To rearrange it to solve for D. We know W. Oh, we don't know W, do we? Whew. So what are we going to do? It didn't work out for me. Is that a big deal? Not really. What do we got to do? Try something else, right? What do you suggest that I try? Oh, with a time of 1 second? Okay. So Rosie's suggesting that we go back to the other way of expressing that given. W is equal to 6,000 in a time of 1 second. Okay, we'll do that if we have to. Okay, there's nothing wrong with that. But since this is the first thought that came to my mind, it's the first thought that came to your mind and probably a couple other people, we'll still see if we can do it this way. And if we have to, we'll go back to that. It certainly works. Okay. It may end up being better. It may end up being more efficient, but I don't think it's going to be the only way that we can do it. Let's just try another equation right now. Power is equal to work over time. Let's try that. Just kind of thinking aloud right now. Work is equal to power times time. Let's go this way, actually. Let's try this. This probably isn't the way you're going to want to end up doing it. We're probably going to want to go back to Rosie's way, but I want to see if we can do it this way here first here, okay? Work, let's say work is equal to F times D over T. No, I don't think that is going to work. I think we're going to have to go back to what you suggested there. So remember we had said when we first wrote down our givens here that we could write down power is 6,000 watts, or we could write down work is equal to 6,000 joules with a time of 1.0 seconds. I think that is what we're going to end up having to do there. Okay, we want to find work. F times D. We're going to say D is equal to W over F. All we're going to do is say 6,000 divided by 200, right? Is that it? Boy, that seems way easier than I was making it out to be. Way easier. Wow. Wow, how to turn an easy question into a hard question, eh? What is that, 30, I think? 30.0 meters. Yeah, boy, oh boy, oh boy. That's way easier than I was thinking. Hey, you know what? I'd like to tell you that I went through that other method just to show you, to demonstrate something. I didn't really. I just, you know, hey, but it does demonstrate something even though it wasn't intended. It demonstrates that sometimes, you know, we overlook what we have to do, right? Sometimes the question is easy, sometimes it's hard. Sometimes we don't do what we need to do right off the top. What happens? Well, we don't get an answer. We try something else. We keep trying something else until it works out, and lo and behold, a really easy solution works out for this particular question.